our project is to see how tumors are growing. And we wanted to monitor if you can see differences between tumors on a very small scale. And in order to do that, I wanted to have a method that was quite precise. And what usually researchers do, we actually put the tumors in mice subcutaneous, and that means like right underneath the skin. And then what you can do is measure how the tumors are growing. And I've done that in the past, but I had a little bit of a problem there because my cell lines are often going a little bit more deeply into the skin, or the inside is a little bit dying, and therefore you don't get proper measurements. So what we set out to do is to find a method with which we could quantify it a little bit more. And that is called iRFP, and that stands for infrared fluorescent protein. And it's a fluorescent protein that you can image using different machines. The problem was that in the institute there was 2 machines, and I didn't know which one would actually be most suitable. And in the past I had used a different machine, and by opportunity I just got to use that machine for 2 weeks on loan as well. So we started out with a pilot experiment with just a few mice, just to see which machine was actually most suitable. And we got quite nice data, and that meant actually that when lockdown happened, we decided, why not get this data accessible for the general public and for everyone to basically see which of these machines would be best suitable for their needs to measure tumors a little bit more accurately.
I guess in a way, the COVID is one of the reasons that this research came out. So a lot of the primary data for this study was collected in December 2018. And we used at the time that internally just to make our own decisions about which platforms we were going to use going forward, and which platforms the Institute should be using. And we always kind of thought at the time, you know, this is data that could go out there, but this really isn't, you know, this isn't and wasn't our primary research. This isn't something that we normally work on. So when the pandemic hit and when we were originally working from home around this time last year, that really gave us a chance to sit down with the data and really get to grips with it and understand what it was saying to us. And it also gave us a chance to really develop further on those ideas to the point where we were able to come back and we were able to make some additional measurements and really kind of round out the paper and round out the comparison between the different platforms. Well, as Patricia said, we've got these 3 different machines that we're trying to compare against each other, if you like. And the interesting thing about these machines is that fundamentally they're all the same. They're almost like having a camera positioned above a mouse who is anesthetized, and we can take a picture of the mouse and it sees in different frequencies. By isolating specifically the frequency that iRFP is in, we can make a map over the top of the mouse of how big the tumor is. And the interesting thing is that when we started to analyze the data, we found that there was quite a big difference in the estimated size increase of the tumor over a period of 2 weeks, depending on which platform you used. And including that, when we measure the tumors physically, we use calipers. And when you measured the tumors physically, we saw a different size increase with those as well. So one of the things that we wanted to determine was, why is this difference? And one of the methods that we used to do that was create a single software package which could read all of the images, because previously each machine had its own software and they're not intercompatible, so you can't make a sort of true assessment based on that. And so I guess the problem we were trying to solve there was really not only sort of which machine is going to give you the best results overall, including the software package, but which machine is actually able to capture the best and most representative data for how these tumors grow. And that's particularly useful because this is a technique that scientists use all of the time. We see lots of different research groups using machines like this and techniques like this to determine the size increase of tumors over time. And we hope that our data, which, as Patricia said, it was never meant to be a paper, it was never meant to be published. We hope that data will help researchers in making the correct decision and the correct choice for which imaging platform is going to work best for them. In terms of overcoming the challenge of introducing as much fairness into the measurements as possible. As I said, one of the key things that we did is make sure that we had the same person measuring using the same software. And we also made sure that that person was blinded as to what they were actually measuring during those time periods. So they knew that they got basically a list of mice that were randomly assigned, and they were just told to measure it to the best of their ability. But the other thing that we came up with at that point was some quite strict sets of rules about how and why you, as we call, gate these images. So you decide essentially which parts of the signal that you get are true signal and which parts are background noise. And we set ourselves up some very specific rules as to how to do that, and then how to apply it across the multiple measurements of one single mouse and across different cohorts and things like that as well. And that really helped us to, I think, produce the best possible data that we could from these platforms. The most interesting bit was really quite how different an answer you could get as to the exact empirical amount of growth happened between machines depending on how you analysed it. And one of the things that we found, which was really quite shocking, was actually depending on the individual who was using the software, we saw quite a big effect in how much growth they were able to measure. And a lot of that's down to lots of very complicated ways as to how the software works, but essentially there's an element of it which comes down to a scientific person's judgment. And now good scientists, of course, will be able to blind themselves and choose images in a random order so that they don't know what it is that they're quantifying, but it can still cause other issues where you can be seeing a group that's growing faster than another group when in reality it's not, or alternatively you see two groups growing at the same rate when in reality there is a difference in how fast the tumours are growing. And when we sort of noticed that, number one, we took steps to correct that within our own paper, and made sure that we always had the same person analysing using the same software. And number two, we then had to think about how to develop our software in a way that was going to cause the least personal choice in the matter and make it the most empirical way to measure things.
When I started this research, I was like, well, which machine should I use? And there was no data available in literature on this. And that's what I think our paper is providing. And I think also the subjectivity of being able to analyze it with the platform that we, as Callum alluded to, have developed is quite useful to get less variability in the measurements. So for that reason, if you get less variability, you would need less mice. So from a triage point of view, I think it is an important publication. And I think I also want to credit Simon Pierce, who has helped with setting up that platform. I think Callum forgot to mention that, because basically within the Institute there was quite a lot of knowledge on how to do this, and he has been instrumental in setting up that platform and actually helping to develop this.
One of the exciting things that we were able to do through this, and as Patricia mentioned through Simon Pierce there as well, was that we were able to make this software publicly available. We were currently sort of talking with Wolfram to be able to put it up onto their platform as well, to make it very open and easy to use. But for now, all of the source code has been published along with the paper, and we hope that it's something that other researchers might be able to use in the future, all the way across the world.
I think what I would like to see is that people are a little bit more careful with how they are, as Callum called it, gating. I think a lot of the times it's very subjective how you do that, and especially with the software from each of the platforms, it's quite hard to determine where to do it. And I think with the platform that we actually created, it's a little bit more easy to decide where you want to put those gating marks.
What I really hope comes out of it is not just specifically people looking at images of mice the way that we are, but also maybe that it provokes a bit of thought and conversation about the research integrity of image analysis in general, and the appropriate steps to take, and limitations as well of some commercial software that's already out there that people can have these discussions.